Okay, can I have everybody's attention? I'd like to welcome our next speaker in our spring seminar series. And this week we have Dr. Reily. Now, Dr. Reily, she is, well, before she came to UHCL, she was an associate professor at the College of William and Mary in Virginia. And then she recently came to Clear Lake about, what, a year and a half ago? Yeah. 2 years ago? And so she came here, and they settled into Clear Lake, and she's actually been working at, in our grants development office and also as an adjunct professor of physics. And she's one of the people who took over from me when I was on sabbatical last semester. So a few of you may have had her in class already. Now, what she's talking about is, I guess, some of the research she's done mostly at William and Mary. And that's about magnetoresistance and how this actually works into technology that we actually use. So I'd like to turn over to Dr. Reily.
Thank you. Thank you. Good evening, and thank you for attending. Can you hear me okay?
We want to close the door.
Yeah, that would be good. Could somebody get the door? Other than that, you can hear me all right? Through the microphone? Okay, all right. I'll be speaking today about something that you use probably every day and you didn't know that, and that's the effect of giant magnetoresistance. And it's used in the sensor in your computer hard drive. But actually when scientists were, when they discovered this effect, that's not the reason they were looking for it. They were studying fundamental physics of electron transport in magnetic materials, and this was something that was discovered as a result of it. And this is a story that takes you through the study of magnetic materials to the first application of what we call nanotechnology. And it is really a wonderful story about how you take science from fundamental research all the way to an application, because giant magnetoresistance was discovered in 1988, and by 1998 IBM had a working prototype of a hard drive based on this effect. And then they were introduced mass market in around the year 2000, and that's when you started to see things like iPods and iPhones, and that was one of the direct applications of giant magnetoresistance. And because of this, because of the important technological applications, the Nobel Prize in 2007 was awarded to the two leaders of the two groups who first discovered this effect. That was Albert Ferrot of France and Peter Grunberg of Germany. And simply the statement that was made for the Nobel Prize was, the Nobel Prize in Physics is awarded to Albert Ferrot and Peter Grunberg for their discovery of giant magnetoresistance. Applications of this phenomenon have revolutionized techniques for retrieving data from hard disks. The discovery also plays a major role in various magnetic sensors as well as for the development of a new generation of electronics. The use of giant magnetoresistance can be regarded as one of the first major applications of nanotechnology. So what I would like to speak about this evening is basically the story of how this came about, and then the people who are involved in bringing this to applications, and basically what it's done for the revolution of the hard drive. Now, in order to take you through this story, first I just want to give a basic introduction to magnetic materials. I wrote this talk for a general audience, so again, I assume that there might be people in the audience who just, again, either need a refresher in magnetic materials, the different types of magnetism. Plus, when I talk about computer hard drives and how they store data, I'll be needing to introduce terms that may not be familiar. So I'll be going over that. And then I'll be talking about the discovery of giant magnetoresistance, basically what led to it, what were people studying at the time. Very important was the development of a technology, the nanotechnology, known as atomically engineered structures. I'll be talking about that a little bit. Giant magnetoresistance, and then how various groups brought this to application, and then GMR and what it did for the computer hard drive. So first, let me talk about magnetic materials. Well, all of you are familiar with the idea that what is the source of magnetism? It's basically a current or moving electric charge. And so you may remember doing this very simple experiment where basically you have a source of current or charge here, a battery, and then you have a coil, and then if you hook the battery up to the coil, what happens? Well, the compass moves. That's because you're creating a magnetic field. And you know from general physics, again, if you have current flowing through a coil, then you induce a magnetic field that looks like this. And that's equivalent to, if you're thinking about a magnet with a north and south pole, it's equivalent to these field lines. And so again, the source of magnetism ultimately is electronic charge. So there's a relationship between electricity and magnetism. Well, also, if you think about the fundamental source for magnetism on the atomic level, it's the angular momentum of electrons in atoms. Now, there's two types of angular momentum involved in an atom. One is the orbital angular momentum, and so this is just a very simple cartoon. It's not accurate, but it just gives you this idea again that one of the sources of a magnetic moment is the angular momentum of the atom, or of the electron in the atom. And the fundamental angular momentum is a true physical property of atoms, even though this is just a cartoon picture here of this orbit. Now, besides the orbital angular momentum, you also have an intrinsic angular momentum of the electron known as the spin. And both this angular momentum, the orbital angular momentum, and the spin angular momentum give rise to atomic magnetic moments. So ultimately, that is the source of magnetic moments, the angular momentum and the spin moment of the electron. So again, you could think of atomic magnetic moment again as being equivalent to a small magnet here with certain field lines. And so here's a definition of the atomic magnetic moment defined in terms of fundamental units known as the Bohr magneton. Now, what happens in a solid? Well, first I just presented a simple picture of one electron atom. Now, if you want to talk about more complicated atoms, like if you go through the periodic table and want to know what are the magnetic moments of the atoms, there's specific rules for filling up the different orbitals of those atoms. I'm not going to go through that right now. But basically, if you go through the periodic table and want to know for any particular atom what its magnetic moment is, it's very straightforward to figure out from the rules of chemistry. What I want to move on to is a solid, though. What happens when you start bringing atoms together in a solid? When you do that, then you think about, again, each individual atom having a magnetic moment due to angular momentum and also spin of the electrons. And usually when you bring all these atoms together in a solid, the moments themselves are not aligned unless you apply an external magnetic field. And if you do that, then you can have several types of response. One is known as diamagnetism. In that case, the moments align themselves opposite of the external magnetic field. And most like materials like water, for example, are diamagnetic. And you don't see much of this effect unless you have a really, really strong magnetic field or a large diamagnetic response, which happens in the case of superconductors. So you may remember those experiments where you have a floating, a little bit of superconductor floating above a magnet. That's because of the diamagnetic response of a superconductor. The other type of magnetic effect that you can have is ferromagnetism. So again, usually the magnetic moments of the solid are not aligned, but you apply a magnetic field and then you can line up all the individual moments. In this case, they're in the same direction of the field. But the type of magnetism that's most important for giant magnetoresistance is ferromagnetism. And this is usually what we talk about when we say a material is magnetic. Now actually there's very few materials in nature that are ferromagnetic, and they're primarily what we call the 3D transition elements. 3D meaning that as you start filling up the atomic orbitals as you go through the periodic table, this is where you start filling up the 3D orbitals. And then also, if you have combinations of rare earth elements, you can also have very strong ferromagnets, which you may be familiar with. Again, if you bought one of these really strong magnets, again, it's made of some combination of rare earth materials. Now, fundamentally, ferromagnetism, again, is when the magnetic moments in the material align by themselves. You don't have to have the application of external magnetic field. Now, why is that the case? Well, the reason this happens is due to a quantum mechanical effect known as the exchange interaction. And it arises for two reasons. It arises because of the Coulomb repulsion between electrons and also the Pauli exclusion principle. Does everyone remember the Pauli exclusion principle? But basically, the idea that you can't have two electrons in one quantum mechanical state. So in the case if you have a single atomic orbital, if you have two electrons in that same orbital, they have to have opposite spins, okay, because they cannot have the same quantum mechanical state, which is defined by the orbital and then also the spin state. Now, if that's the case, though, these electrons in the same orbital have close proximity to one another. And the Coulomb repulsion energy is very high in that case. And you can estimate it here just simply from basic physics here. This is the Coulomb potential energy, just using a typical separation in an atom. And that comes out to be 10 to the minus 18 joules, which if you convert that to temperature, that's 10 to the 5th Kelvin. So that's an extremely high temperature. So this Coulomb energy is very high. So naturally, then what happens to lower that energy is the natural alignment in this case is, or for example, if you're filling up atomic orbitals and accounting for the spins, you'll have one spin state in this orbital, then the next electron will fill the next highest orbital, taking on the same spin. So that effectively then will separate the electrons and lower the expulsion, Coulomb expulsion energy. And so if you walk away with anything from this talk, it's basically the idea that what nature tries to do is minimize energy. And that's very true of magnetic materials. That's my husband watching the Super Bowl. So this exchange interaction, you can also describe it, again, this is a quantum mechanical effect. And so this is actually a very good graduate quantum mechanics problem if you've seen this yet in your quantum mechanics course. But basically you can talk about now a single atom with two electrons with two spins, and then calculate now what the energy will be, and then also what the exchange energy will be, or how much the energy will be lowered by having these two electrons aligned, having the spins aligned. And so again, to calculate the energy, it's just given by this expectation value. And the exchange energy itself, if you go through the calculation, what you'll find is that it will be equal to minus 2 times J. This is known as the exchange value or the exchange integral. And then you have the spin of one electron and the spin of the second electron. Now, for the particular types of interactions for ferromagnetism, this exchange integral is positive. So the lowest energy state is to have then all these spins aligned in the same direction. But you can also have the case for materials where the spin, this exchange integral is actually negative, and so the lowest energy state will be an anti-alignment, and that's known as anti-ferromagnetism, and that's important later on when I talk about the GMR multilayers. Now, another very important property of magnetic materials is domains. And again, this comes about from that principle that nature likes to minimize energy. Now, I just told you that ferromagnetic material, like if this was a piece of iron, the magnetic moments like to automatically align with one another. But what ends up happening then is it produces a large magnetic field, and there's a lot of energy in that magnetic field. And actually what the magnet will do to itself is it will demagnetize itself. And how it does that is basically by forming domains. So then what you'll have is one region with all the spins pointed in one direction and another region with all the spins pointed in the other direction. And you see that immediately minimizes the fields and minimizes the energy. And then the magnet will keep doing this until in the end, if you take a piece of iron out of the ground, its natural state will be like this. It will not be very magnetic. You have to actually you have to heat it up and apply a very strong magnetic field to actually get it into the state where it has a strong external magnetic field. In the same way, if you had a magnet that was very strong and you heated it up and cooled it down, its natural state again would be to break up into these magnetic domains. Now these domains end up being very important for magnetic storage. I'll talk about that in a moment. But if you're wondering what I left you with here by your chair, this is actually a demonstration of two things. One, it's a demonstration of magnetic domains. And second, it's a very simple illustration of how your hard drive works. This is just simply a refrigerator magnet, and I just cut a little piece off of it. This little piece will serve as your sensor, and if you drag it across the magnet in this direction, you'll feel the piece jump up and down. And what you're feeling there are the different domains in this refrigerator magnet. Because when they make these magnets, the process by which they make them, they roll out this material. It ends up producing domains, longitudinal domains along this refrigerator magnet. So again, this is one way you can actually feel domains, and later on I'll show you that this is the way that your computer, the sensor in your computer will read your hard drive. Now another very important property in magnetic materials is hysteresis, and that simply means magnetic memory. And so when you have a piece of magnetic material or a thin film of magnetic material and you cycle it through a magnetic field and you measure the total value of magnetization, what you'll find is that each time you do this, you end up with the same curve, which is very fortunate for magnetic memory, because if this wasn't true, then magnetic memory wouldn't work at all. But the idea again is you can cycle the magnetic field back and forth, and you'll end up now, the value out here, this is known as the saturation magnetization, and beyond this point, it doesn't matter how strong the magnetic field is, you're not going to get any more magnetization out of the material. When you're at this point, all the magnetic moments are pointing in the same direction in that material. Now, as you start to lower the field, again, from that idea of the minimization of energy, the magnetic material will break up into domains, and you'll actually cross a point where the total magnetic moment is zero. And so it looks like this. The different moments now are pointing in different directions and canceling each other out. If you apply a field in the opposite direction, then you saturate it in this direction, and then you just step through the curve again. And you can do this again over and over again and end up with the same state here, and pretty much the same curve each time you trace it. Here's a picture of actual domains in a thin nickel film. So again, if you were to look at this, there's certain types of microscopes that let you look at this, or using magnetic force microscopy, you can also trace out these magnetic domains. Now, one other very important property before we talk about giant magnetoresistance, or which contributes to giant magnetoresistance, is spin-dependent transport. Before 1988, or I should say, actually, the whole idea of spin-dependent transport is actually very old. This was discovered by Lord Kelvin in 1856. But the actual application in electronics didn't happen until after the discovery in 1988. Before then, all electronics was based simply on the charge of the electron. As you know, when you learned about electronics, you never had to worry about what was the spin of the electron. It didn't matter. It was just how many electrons you had, what was the current. Well, now, with giant magnetoresistance and with some of the newer properties that are being discovered and the newer devices that are being developed, you do have to consider the spin of the electron. And this was actually known for a very long time. And one of the properties that demonstrates this is magnetoresistance, or simply magnetoresistance, but it's also known either as ordinary magnetoresistance or anisotropic magnetoresistance. That's to separate it from later on when we talk about giant magnetoresistance. Now again, this was discovered in the 1800s, and basically what Lord Kelvin did was he had a piece of, I believe he did this on iron and nickel, and this is a more complicated setup than he had. Obviously, he didn't have a digital voltmeter. But in this case, this is a very simple lab experiment that you can do. It's known as a 4-point probe measurement. In this case, you have an ammeter measuring a current, some type of current source, and then a voltmeter measuring the voltage. And simply from Ohm's law, V equals IR, from here you can deduce the resistance. Now for magnetoresistance, you're going to apply a magnetic field either in this direction, perpendicular to the current, or parallel to the current. And what you'll actually find is if the magnetic moment is initially pointing perpendicular to the current, as you apply the magnetic field along this direction, you'll see what will happen is the resistance will actually drop. Now this effect is about 1 to 2%. It's not a very large effect, but it's enough of an effect that you can measure it. So again, this is known as magnetoresistance, and this essentially is an indication that the spin of the electron is important in electronic transport. Now why is this the case? Well, it's because what is resistance caused by? When you think about electrons moving through a material, Resistance comes about because there's defects in the material, or there's things for the electrons to scatter off of. Now, scattering just doesn't happen randomly. If you think about it quantum mechanically, in order to have a scattering event occur, that electron is in one state. It needs another state, quantum mechanical state, to scatter to. If there isn't that second quantum mechanical state to scatter to, then you will not get the scattering event. Now, how does spin play into this? Well, if you think about this in terms of a band diagram, for a normal material like copper, the amount of spin up and spin down electrons is equal. Okay. The material is not, there's no automatic alignment of electrons or magnetic moments in that material. So scattering will occur equally for both down and up electrons. And again, because you can think about it from this diagram, what this indicates up here is that there's empty states here for the electrons to scatter to. However, in a material like iron, nickel, or cobalt, here in the D band, the favored state is up or aligned. And so all these states are going to be filled. That's what this band diagram means here, where the states down are not going to be filled, completely filled. So what this means then is that electrons that have spin, and up and down is defined relative to the magnetic field. So the electrons that have the spin opposite of the applied magnetic field are going to scatter more, and they're going to have a higher resistivity than the spin-up electrons. Now again, this whole concept of spin-dependent scattering was actually well known before 1988. And you go to the next slide here. In fact, Neville Mott had a model for this. This was known as the two-current model. So again, very simply, if you're thinking about resistance in the material, the downspin electron is going to have a lot of scattering events as it moves through this material, but the spin up electron is going to have less of an effect. So if you want to diagram this in terms of a resistor model, in comes your current, the spin up electrons are going to have a smaller resistance than the spin down electrons. And actually this model is quite true, and I'll show you later on that this is used to describe giant magnetoresistance. Okay, so I've given you the background now to tell you the story of giant magnetoresistance. Now, Albert Ferro, who's credited with the discovery of the giant magnetoresistance effect, along with Peter Grunberg, his thesis topic was dealing with spin-dependent transport in magnetic materials. He was very interested in magnetic materials themselves, and also, again, how electrons are transported through magnetic materials such as iron and cobalt. However, scientists were limited before the 1980s by the types of materials that they were able to study. But a revolution happened in the 1980s, and that was the development of deposition techniques or material growth techniques that would allow you to build a material essentially from the ground up. This was the first application of what we know as nanotechnology. Nano meaning, again, this is on the nanometer length scale. Before then, there were a lot of thin film growth techniques, but you weren't able to control the growth on an atomic level scale. What I show here, so again, this is just a general illustration of the technique where you want to lay now atomic layers down one by one and control the deposition to a single atomic layer. And this is actually possible. This is a cross-section of a type of film. This is cobalt and tungsten, I believe. Let's see where. But what you see here is you can almost make out the atomic resolution of these individual layers. And each of these cobalt layers is only 3.5 nanometers thick, which, to give you a length scale here, this is a virus. Okay, I think it's the flu virus. Basically, if you think about the size of a virus, that you're dealing with deposition on a much smaller length scale than this. So this was quite a technological advance. And the way that this was done initially was a technique known as molecular beam epitaxy. And this is a very precise, very complicated technique where you need a vacuum chamber where you're getting down below 10 to the minus 9, 10 to the minus 10 torr. Okay, so you're talking about vacuums that like you would experience in outer space. And then depositing the materials by what's known through an infusion cell. And this is basically, you heat up an atomic material or a molecular material and you end up spraying it basically onto your substrate with a very fine resolution. This is known as molecular beam epitaxy. There's also other techniques for growing these materials, such as sputtering. I'll mention that in a moment. Now, because of these precise techniques, scientists got really excited because they said, you know what, we can build materials from the ground up. And Albert Ferret and Peter Grunberg's groups, what they were really interested in was magnetic properties. What would happen if we grew thin iron layers separated by chromium? Now, chromium is a non-magnetic material, and iron is a magnetic material. So one of the questions was, how are these iron layers going to talk to each other through this non-magnetic material? That was the first interest that they had in these multi-layers. So one thing they found was that depending on the thickness of the chromium, you could control the interaction between these iron layers, that these iron layers would actually talk to each other. And for this particular experiment, they would align themselves in an anti-ferromagnetic arrangement, and you can control the amount of that, the strength of that interaction by the length of the thickness of the chromium layer. Now, in other cases, you could actually, depending on what material you chose, you could go between a ferromagnetic interaction to an anti-ferromagnetic interaction. So this was Peter Grunberg's contribution to the discovery, the first contribution to the discovery of giant magnetoresistance, because you really need these layers now to couple to one another in order to see this giant magnetoresistance effect. So 2 years later, in 1988, the group of Albert Ferret, they were studying these iron-chromium layers. And his group decided, well, let's measure the magnetoresistance in a material like this. And what they found, to their surprise, was they saw a huge effect. Now again, ordinary magnetoresistance is 1 to 2% change in resistance. This data showed a change of up to 80%, hence the name giant. And when they showed this at the APS meeting that year, everybody was excited. They're like, wow, we've never seen anything like this before. This is incredible to get this kind of effect. And they immediately gained the interest of people from IBM, because they saw the application of this, because at the time magnetoresistance was what was being used in the computer hard drive sensors. So if you have something that's giving you an 80% response versus a 1% response, that's pretty exciting. And Peter Grunberg's group also measured magnetoresistance, and they reported results in 1989. And again, just to show you, it's a very straightforward experiment. You just have some leads on your thin film, apply a current, measure the voltage, and from that measure the resistance. And then measure the resistance then when you have a state of parallel alignment, anti-parallel alignment versus parallel alignment. And you cycle between these two by the application of magnetic field. But this anti-ferromagnetic alignment is key for this, because if the material didn't take, if these multi-layers didn't take on that automatic alignment, you wouldn't see this large effect when you applied the magnetic field. So that's why the coupling is very important. So that was the discovery of GMR, but the person or the group that was really key from bringing this to the laboratory to applications was a group at International Business Machines, IBM, and particularly Stuart Parkin and his group. After this effect was discovered, he immediately went in the laboratory with his team of postdocs and technical scientists. And I had heard what they did was they just basically went through every material that they were able to find to test what would give the largest giant magneto response, to learn how to basically understand and maximize the effect. And this group at IBM discovered many things in regards to what were the best materials to use, the best magnetic materials, what types of geometries were best to use. And so what I show here is, actually this is a demonstration of types of chambers that they were using to study this, so you can see it's quite complex. And actually the technique, so this was either done through molecular beam epitaxy. There's also a technique known as sputtering that doesn't require as high of a vacuum. And so it's actually better when you're talking about an industrial process to use sputtering. So one thing that Parkin's group did was they came up with a geometry that was much better to apply in technology. Because one of the problems with the multi-layers was you had to have such fine atomic control through molecular beam epitaxy to achieve that optimal anti-ferromagnetic alignment to see the giant magnetoresistance effect. That just wasn't acceptable when you talk about mass producing this for a hard drive. So what they developed was something known as a spin valve, and this is actually what's used in your computer hard drive. The spin valve consists of just two ferromagnetic layers separated by a non-magnetic layer. So this is typically something like cobalt, copper, and cobalt. So again, this is much simpler because you're only dealing with 3 layers. What you do is you pin one of these layers magnetically, and that's done through by growing this against another material. And then you allow the other material to freely rotate in the magnetic field. Excuse me. And so what you'll see then is if you have parallel alignment of the ferromagnetic films, one spin state will basically sail through these layers with very little scattering. So this is a low resistance state, where you have the anti-parallel alignment. Both these spin states are going to scatter. This is a high resistance state. Excuse me. So here's what the data looks like. The reason it's called a spin valve is because it basically has an on and an off state, which is really great, again, when you want to use this for a sensor, because you know exactly what values you're going to get for on and off. The next major step in the development of the application of this in the hard drive was to apply the current perpendicular to the layers. In fact, the last slide that I showed you here showed you the cartoon of the spins or the current traveling in this direction. And this was pioneered by a group at Michigan State University, Bass, Pratt, and Schroeder. And what they did basically through a growth technique, they laid down first a contact layer, then they grew the magnetic multilayers, and on top of this grew another contact layer. These contact layers were made of superconducting niobium in order to make very sensitive measurements of the electronic properties of these thin films. So again, the idea was to send the current here perpendicular through this multilayer, this spin valve. And the benefit of this, one of the benefits is that the total resistance of this sensor here is inversely proportional to the area. So as the area decreases, the resistance goes up, and also the effect that you measure will go up. It becomes much easier to measure the giant magnetoresistance effect when you have a higher resistance. And so my role in all this was I actually did my postdoc at Michigan State University, so one of the things that I did was I measured the response of some materials, particularly cobalt and copper, to test, excuse me, so the source of giant magnetoresistance, independent scattering. I showed you this cartoon before. So the idea is that one spin state will scatter more than the other, depending on the alignment of the magnetic layers. So when you cycle through the magnetic material here, you get this result. So let me go on to the application and how this is actually used in a computer hard drive. Now, how your hard drive actually stores data. How many of you have actually taken apart a hard drive? So you know what's inside. I have a platter that's made up of multiple domains. This platter is spinning around at a high rate of speed, and this read head's moving back and forth, and what it's reading is individual magnetic domains, or magnetic particles. Depending on the orientation, that's how your data is written onto the hard drive. It's written in binary codes, so one orientation is a 0 and the other orientation is 1. So for example, if you have a lot of text, that's just written out here in terms of a accepted code, a binary code of 0s and 1s. Now when you talk about bytes and kilobytes and gigabytes, that's actually talking about the actual number of physical bits on the hard drive. If you have a document that's 1 kilobyte, that's 1,000 pieces of information. Again, you can go up to megabytes and gigabytes. Gigabytes, that's 10 to the 9th pieces of information, individual domains that your papers or whatever you're storing on your hard drive is written as. So when most people, when their computers don't work, they get upset But I'm amazed even every time this thing works, just given how complicated this is when you think about it. Now the reason that this can shrink and you can get more data onto a hard drive is the sensor here. If the sensor is more sensitive, then these bits can shrink and you can get more of them onto the plat. So that's essentially why we want to develop more sensitive read heads. This is a picture here, a magnetic force microscopy image of an actual hard drive. That's the 750 gigabit hard drive, showing you the individual domains or the individual bits on that hard drive. And again, to give you a length scale, this is about 1 micron by 1 micron, and here's our little virus here, just to give you a length scale of how small this is. It's just incredible when you think about it. Now, it's really interesting when you think about the evolution of the hard drive, because the very first hard drive was developed by IBM, and I'll show you a picture of it in a moment, but you could store, I think it was about 4 megabytes, and it was stored on 50 24-inch hard disks. So that's where we started from, and now we're up here, and this curve here is actually old. It's from 2006 or so. Now I've seen standard hard drives that are a terabyte. It's just incredible where we've come. And this is essentially because of the sensors that are used in the hard drive. So you see here around the year 1985 or so, you have this jump here. And this was the introduction of the use of magnetoresistance as a sensor. Okay, so just simple 1 to 2% magnetoresistance effect. And then later on here, the first GMR head came out, I think, in 1998, 1997. And so again, then you see another kink in this curve here with a dramatic evolution in the hard drive memory. But not only did the introduction of GMR allow for this increase in areal density, it also allowed for the hard drives to shrink. So here's a picture of the very first hard drive, 1956. And so again, you got 4 megabytes. Are there any of these left anywhere? Has anyone ever seen one of these? I'd love to see one of these. You could store 4 megabytes on 50 24-inch diameter disks. So and you could lease it from IBM for $3,200 a month. But now, when you think about in 2004, when you started to see the iPods and iPhones introduced, you're getting gigabytes of memory onto hard drives. And yes, that is a hard drive. If you pull apart your iPod, well, I wouldn't recommend it, but or your phone, you'd find a very tiny little hard drive in there, storing several gigabytes of data. And in there is a giant magnetoresistive sensor. So what I'd like to do now is, I think the best demonstration of this is to actually show you some animations. Do I have enough time for that? If you go to IBM's website, they'll actually, they give you here some nice animations. So here's your hard disk. If you zoom in here, this is basically what the sensor looks like on the bottom of your read head. Okay, you have this inductive coil, this is the write head, and then on the bottom here, we even have to go smaller than that. That thin film layer that I was talking about, here it is. And this is the magnetoresistive sensor that they used to use. So what it shows you here is as it's running over the bits, you see each bit has a magnetic field, so it's altering the magnetic moment in the material and giving you a change in the resistance. So each little blip in resistance corresponds to a bit. But when you use giant magnetoresistance then what you're doing is you're using one of these multi-layer structures. One of the magnetizations is pinned, the other one's free to rotate, and you get a much larger blip or response in the resistance. So again, you can shorten, or you can decrease the actual size of the bits that you're sensing. And if you want to see how giant magnetoresistance actually works here, they have this nice animation. It basically shows you, this is the low resistance state when all the magnetizations are lined parallel to one another. So you have a low amount of scattering. You see what comes with sound here. So, when you align this, when this goes over a bit and then realigns this magnetic moment, then the electron scatters, but I don't think it makes that kind of sound. is basically animation of the giant magnetoresistance effect. So to end here, what I'd like to do is just show you a 7-minute movie that was produced by the Nobel Prize Committee about all this, so just as a summary. Actually, I should ask, did everybody see okay with the lights on? How do I control it? Oh, on here?
Oh, no, I think I got it.
Physics and jazz go well together, Albert said. Along with Peter Greenberg, he won this year's Nobel Prize in Physics.
He's got his iPod.
They are renowned for their work in the field of spin-based electronics, or spintronics.
Spintronics is an electronics exploiting the spin of the electrons. And so this is a work coined by physicists, and then this musician, Laurent Deville, had the idea to name one of his compositions Spintronics, because he knows many and he knows my research.
Albert Fert's research has led to applications that are now meaningful to music lovers everywhere.
Yeah, it is always surprising and gratifying to see that what we had in mind before now is something concrete in the everyday life. Okay, this is surprising, and this shows that the science is working. No problem, it works.
The science works so well that applications related to the discoveries of this year's laureates in physics are essential to our world of data retrieval. From music libraries that fit in your pocket to the mind-boggling storage in your computer. The science that made this possible derives from the work of Albert Fert and Peter Greenberg. Working independently, they discovered a way to make extraordinarily sensitive readout heads for hard disks. Information is stored on a hard disk in microscopically small areas with a certain magnetic direction. The readout head scans the magnetic information, and an electronic device turns it into information we can use.
In a way, we were lucky, but then I also remember something which my mentor always said: everybody can be lucky, but those who are able and capable and work hard can make use of their luck.
This occurs frequently in science. Okay, some breakthrough appear when by the meeting of two different domains at the interface between two domains of science. In this case, it was a meeting between fundamental research and progress in technology.
By alternating layers of magnetic and non-magnetic material, Peter Greenberg and Albert Fert discovered a totally new physical effect dubbed Giant Magnetoresistance, or GMR. GMR is an effect related to the upspin or downspin of electrons. The magnetic field in the layered material was discovered to influence the resistance or passage of those electrons through the layers.
It's that the mobility of electrons in the magnetic material depends on the orientation of the spin with respect to the direction of the magnetization.
We started to work on this and built up all the equipment.
Then we have optics consisting of mirrors, prisms, lenses.
And when we were ready and measured, we indeed found this new effect.
There was a spontaneous alignment in opposite direction of the magnetization of the higher layer. And so I jumped on these results. So we begin to work on this discovery of Peter Greenberg and the new technologies.
We met at a conference in France, in Le Creusot, and compared our results.
I always say that the discovery of the general magnetism has been by both of us.
It was a steady process of basically being interested in what happens in the system and not having a long-term perspective on some applications.
Both, Peter Greenberg and Albert Fert were able to extract all the physics and the implication of this, to synthesize, to interpret the results, bring them to new fields, emerging fields like and also participate to the development of application. I mean, there are very few people in the world that are able to do this.
I was simply a good student, but maybe afraid by the world of research, the world of physics. I was not so confident. But I began to be confident when I see physics works, that you can imagine something and you can predict some result of experiments. This proved me that physics is working well.
I must say most of the puzzles which I met during my life as a scientist here, as a researcher, came by biking, when I was biking. And I remember clearly various ideas came when I was biking around our lab, and then I suddenly had the idea, oh, when we discovered a spin wave, and first we got the spectra for some leads, we were very much puzzled about that. And the idea how we should interpret this came to me when I was riding my bicycle, that I clearly remember. I think I'm very easy to get enthusiastic about something. I'm playing guitar or I find a song, I very much like it, get enthusiastic about it. So I think this is an important property also for science. When you think, oh, this is great, this is interesting.
It's this very enthusiasm for science, the spirit of exploration, experimentation and openness that helped propel Peter Grunberg and Albert Ferret to a Nobel Prize.
I was in a meeting but I knew that there was a time for the announcement, so I had the mobile phone in my pocket. It was a shock. Then I went out from the room and so many people looking for me.
I was in my office, and suddenly my assistant came running into my office and there's a phone call for you. That was a great moment.
I don't think I can say it any better than that, so thank you very much.
All right, questions?
Yes.
That seems to be half the story. You've also got to shrink the size of domains. Is that easy?
Well, that's a whole nother story, actually, because that's one of the areas where they're running into technical challenges, because as you shrink the domains, what happens, the ferromagnetic material actually turn paramagnetic. So they're trying to work around that by the design of the domain, or the actual using, like, again, the nanotechnology to make small magnetic materials, magnetic dots that retain, that have a single spin state and retain that when they're so small. So that, yes, that's a whole another area of development that I didn't really touch on. Yes. Yes, I'm glad you brought that up. I didn't put any of that into the talk, but that's one of the other large applications of the Magnetoresistance, is to produce just sensors, so not just for hard drives, but like one application was Ford Motor Company wanted to put these in cars to sense gears, for example, or like your timing gear, your timing belt, to see if it was starting to wear. The idea is it had ferromagnetic material moving around, so if you had a small magnetic sensor there, you could sense the gear moving around. But yes, there's been applications like that, or using sensors, yes, to sense small magnetic fields, like the Earth's magnetic field. Also for storage devices, there's a company called Non-Volatile Electronics, and you mentioned Honeywell, and I think they have put some of these things on satellites, actually using the magnetic, using these multiple layers to store data in a non-volatile way. So meaning you don't need an application of a current to keep them. I know that's a whole other area of application. Well, maybe if you coupled it with a plasma in some way, of a plasma. Well, the hard drive always uses a mechanical device, but I believe the flash drive technology. That's just through writing currents, grid of wires. Not so knowledgeable of this as I am of the hard drive, but yeah. So there's advantages of that, obviously, that you're not going to have failure. But then there's other advantages of the hard drive. I think the hard drive is still better for reliability, data density, but they're really two competing areas, right? The flash drive. In fact, I think now the iPhone's flash drive.
There's a big price difference, though, because if you want to get like 128 gigabyte solid state drive for a laptop, I think it's going to add like an extra $1,000 to the price over getting an even higher capacity hard drive.
Questions? Well, you can take this home with you if you want. And again, as a demonstration of a hard drive, so this would be like your read sensor running across your data here. So,
okay. All right, let's thank our
impress
speaker
your
again.
friends.
Also, just a reminder, there's no talk next week because I'm not going to be here with the APS meeting, and so the next speaker is going to be here on February 22nd, and that's going to be our Shapley lecture, and we're going to have a speaker, Eric Linder. He's going to be coming in from the Berkeley Center for Cosmological Physics and in Lawrence Berkeley National Lab.